Welcome to our video lecture on relative atomic mass. We're going to do a lot of math and a lot of periodic table time in this lecture, so definitely grab a calculator and your periodic tables if you don't already have those out and nearby. All right, here we go. Our objectives for today are to use the periodic table to find and calculate masses of atoms, molecules, elements, and compounds. We're going to start to understand this idea of the mole number, and then we're going to use molar mass and the mole number to calculate the numbers of atoms or molecules in a sample, and then we're going to get to the big picture of this lecture, which is calculating relative atomic mass given isotope abundance and mass. All right, so let's review atomic mass really quickly. Remember that on your periodic table you have lots of information. You have the atomic number. This is the number of protons in each atom of an element. You've got your element symbol and element name, and then you also have this relative atomic mass. Relative atomic mass is given to you on the periodic table. And so if my question is, what's the mass of one atom of carbon? I'm going to find carbon in the periodic table. I'm going to use that mass number, that relative atomic mass, and 12.011 is our answer. Our unit for atoms is AMU, which stands for atomic mass unit. So the mass of one atom of carbon is going to be 12.011 AMUs, atomic mass units. The mass of two atoms of carbon, I'm just going to take that number, 12.011, and I'm going to multiply it by 2. And so now the mass of two atoms will be 24.022 AMUs, atomic mass units. What if I wanted to know the mass of 1,000 atoms of carbon? I'm going to take that 12.011, I'm going to multiply it by 1,000. And I'm going to get 12,011 AMU, the mass of 1,000 atoms of carbon. All right, so what if instead of 10 or 2 or 1,000, I had this crazy big number, 6.02 times 10 to the 23rd atoms? I'm going to do the same thing. I'm going to take my 12.011 multiplied by 6.02 times 10 to the 23rd atoms of carbon. The mass of one atom of carbon, the mass of that many, 6.02 times 10 to the 23rd atoms of carbon. I definitely need my calculator for this one, so 12.011 times 6.02 times 10 to the 23rd power, and I get 7.23 times 10 to the 24th AMUs. But what if I want to convert my AMUs to grams? I'm going to use my railroad tracks. I have AMUs on the top. I'm going to put AMUs on the bottom. 1 AMU is equal to 1.661 times 10 to the minus 24 grams, because that's what an AMU is equal to. So now back to my calculator. I'm going to multiply everything on the top. 7.23 times 10 to the 24 times 1.661 times 10 to the negative 24 divided by 1, and I get 12.01 grams. You might be thinking that number looks super familiar because it's almost the same as that guy. And if I had kept more sig figs in this answer, I would have gotten even closer to my 12.011 grams. So this is the magic of the periodic table. The mass number given to us, that relative atomic mass, is the mass of one atom in AMUs. It's also the mass of 6.02 times 10 to the 23rd atoms in grams. And this idea of 6.02 times 10 to the 23rd is what we call the mole number. Moles are super important in chemistry. The atomic mass number on the periodic table is equal to the mass of one atom of an element in AMUs, and 1 mole, and 1 mole is equal to that number, 6.02 times 10 to the 23rd particles of the element in grams. This number, 1 mole, is equal to 6.02 times 10 to the 23rd. You don't have to have memorized because it is on your handy-dandy reference pages on the back of the first piece of paper under Constants and Conversions. Avogadro's number is also known as the mole number, and it's how many particles are in 1 mole. The mole number is also known as Avogadro's number. This is Amadeo Avogadro. He did some super cool chemistry stuff that we'll talk about when we get closer to gas chemistry in the spring. Avogadro's number is the mole number, and it tells us that there are 6.02, 602 septillion things, 6.02 times 10 to the 23rd, atoms or molecules or ions or any other thing that I want to put in there, 6.02 times 10 to the 23rd atoms in 1 mole. All right, so what is the mass of 1 atom of gold? We're going back to the handy-dandy periodic table. The symbol for gold is AU. Its mass number is 196.967. And since I'm looking for the mass of 1 atom, the unit is going to be AMUs. What's the mass of 6.02 times 10 to the 23rd atoms of gold? Well, I could do this times this. And then I could get some big number, and I could convert it to grams, or I could remember that this is equal to 1 mole. And I know that my mass on the periodic table is equal to the mass of 1 atom of that element in AMUs, or it's equal to the mass of 1 mole of that element in grams. And a mole is equal to 6.02 times 10 to the 23rd. So I don't actually have to do all that math, because I know that my final answer will be back to that same number, but instead of in AMUs, now it's going to be in grams. But what if I want to know the mass of 1 mole of gold? Oh, my friends, we don't even have to look at the periodic table again, because I know that 1 mole is the same thing as 6.02 times 10 to the 23rd. And so if I have 1 mole of gold, I have 6.02 times 10 to the 23rd atoms of gold, and that means that my mass is the same number one more time, but since it's moles, it's grams. Atoms in AMUs, moles in grams, and because a mole is equal to 6.02 times 10 to the 23rd, this is also that same number in grams. Let's practice some more. So now we're going to add another complex piece. Instead of looking at just 1 atom of an element, I'm going to look at a molecule of a compound. This compound is water. Water is H2O. To find the mass of 1 molecule of water, I'm going to add 2 hydrogens, and there's an invisible 1 right there, 1 oxygen. Hydrogen is here. The mass number is here. So hydrogen is 1.008. I have 2 of them, so I'm going to multiply this by 2. And I'm going to add 1 oxygen, which is here, 15.999. I add those up, handy dandy calculator. 2 times 1.008 plus 1 times 15.999 gives us a mass of 18.015. Since I'm looking for the mass of 1 molecule, which is atoms stuck together in chemical bonds, my answer is going to be in AMUs. The mass of 10 molecules of water, I'm just going to take that number and I'm going to multiply it by 10, and I'm going to get 180.15 AMUs. But what if I wanted to know the mass of this 6.02 times 10 to the 23rd, 602 septillion molecules of water? I could take this number and multiply by that number, or I could remember that this is my mole number. And if I have the mole number, I'm going to go back to that mass, 2 times 1.008 plus 1 times 15.999. That's going to equal 18.015, but instead of AMUs, it's going to be grams. So I'm going to use the same number, 18.015, which is the sum of those 2 hydrogens and 1 oxygen, 18.015, but instead of AMUs, we're going to use grams. But what if I want to know the mass of 1 mole? It's another trick question. 1 mole is exactly the same thing as 6.02 times 10 to the 23rd molecules, and so my answer will be the same thing, 18.015 grams. Good? So what if I now have 16.3 grams of sulfur and I want to turn that into moles? The last couple questions I said, how many grams in a mole? And now I'm asking you for how many moles in a gram. We're going to go backwards. And we're going to use our railroad tracks. So 16.3 grams of sulfur is what I'm starting with. I want to get rid of those grams and turn my grams into moles. What do I know about grams and moles? Well, I know that the periodic table tells me how many AMUs in an atom and how many grams in a mole. I need to know this. Ooh, that was a very strange start. I need to know this, how many grams in a mole. So the periodic table tells me that there are 32.066 grams in 1 mole of sulfur. Why did I put 32.066 grams on the bottom? Well, it's because I have grams on top and I want those grams to go away, so I'm going to put grams on the bottom. Grams on top and grams on bottom cancel out. I'm left with a unit of moles, which is what I'm trying to find. So with my calculator, I'm going to multiply across the top 16.3 times 1 divided by the bottom 32.066. So with my calculator, 16.3 times 1 divided by 32.066, and we're going to get 0.508. 3265764, lots of decimal places. I don't want to keep all those. We're going to count our sig figs. We have 1, 2, 3. We have 1, 2, 3, 4, 5. You might be thinking, and we have 1, and we only keep 1 in our final answer. But here's a weird thing. This is actually telling us that exactly 1 mole is equal to this molar mass. I rounded this molar mass. I could have added more sig figs, but this is 1 mole defined. The periodic table tells me the mass of 1 mole. Not I rounded to about a mole, but it could have been a half a mole is equal to this mass. No, my friends, exactly 1 mole, which means that this 1 is not 1 sig fig, but it could be 1.00000000000 mole, or it could have been 1.0000000 infinite numbers of zeros mole, because this is a definition. And so this 1 mole, because it's a definition of molar mass, is actually an infinite number of sig figs, which will not be the least number. So we're not even going to worry about counting that. Instead, we're just going to count 1, 2, 3 here. We're going to count 1, 2, 3, 4, 5 here. 3 is smaller than 5. We're going to keep 3 sig figs. 1, 2, 3. That 3 is going to do nothing to that 8. So my final answer is 0.508. My unit label is going to be moles because my grams canceled out. Unit label moles. And this is my final answer. But what if I now want to figure out how many atoms of sulfur my 16.3 grams is equal to? I'm actually going to start with this number, my mole number, 0.508, 8 moles of sulfur. I want to turn my moles into atoms. I'm going to put moles on the bottom. I'm going to put atoms on the top. How many atoms in a mole? Well, if we remember back a couple slides, Avogadro's number tells us that there are 6.02 times 10 to the 23rd particles per mole. Per mole means in every 1 mole. And so I'm going to put 1 mole on the bottom, and I'm going to put 6.02 times 10 to the 23rd particles, and atoms are a kind of particle, on the top. And so top and bottom, moles cancels out. I'm going to multiply across the top. I'm going to divide by that 1 on the bottom. And with my calculator, I get 0.508 times 6.02 times 10 to the 23rd. And my answer is 3.0601259 E23. What does this even mean? And how many sig figs do I get to keep? So I've got 1, 2, 3 here. I've got 1, 2, 3 here. Do I have 1 here? No, because again, this is definition. The definition of a mole is 6.02 times 10 to the 23rd particles. So this one also has an infinite number of sig figs. So I'm going to keep 1, 2, 3 because 1, 2, 3 is the same. 1, 2, 3, that 0 doesn't do anything to that 6, 3.06. Don't forget I've got this quirky stuff back here, E23. That means times 10 to the 23rd. My unit label is atoms. I have 3.06 times 10 to the 23rd atoms of sulfur in my 16.3 grams. This makes sense because I had about half a mole, remember? And about half of 6.02 is about 3 times 10 to the 23rd. Atoms of sulfur is my final answer. Good? Good. All right. We're going to do another one like this, and then we're going to flip over to the idea of relative atomic mass. All right, so during a chemical reaction, 32.7 grams of carbon dioxide, CO2, is produced. How many moles of CO2 is this? So I'm going to set up my railroad tracks. Whoa, that was a terrible 3. 32.7 grams of CO2. I need to get rid of my grams and turn my grams into mole. I have grams on the top and grams on the bottom, so it cancels out. Turn my grams into moles. What do I know about grams and moles? I know that my periodic table tells me how many grams are in a mole. So I'm going to go to my periodic table, and I'm going to find carbon is 12.011, and oxygen is 15.999. Carbon, I have one of those, so I'm going to do 1 times 12.011. I'm going to add to that my 2 oxygens 2 times 15.999. Carbon's 12.011, oxygen is 15.999. So with my calculator, I'm going to do 1 times 12.011. I'm going to add to that 2 times 15.999, and we get a grand total of 44.009. Remember that the mass on the periodic table tells us how many AMUs in an atom or a molecule if we're talking about a compound, and it tells us how many grams are in a mole of that compound, and that's the number that I want. So I'm going to throw grams at the end of this. This is the number that I'm going to put next to grams on the bottom to get grams to cancel out, and the periodic table tells us how many grams in 1 mole. So now I can cancel out grams, top and bottom. I'm left with moles. We're going to get out our calculator, and we're going to do 32.7 times 1 divided by 44.009, and our answer is 0.74302983848. So many digits. I'm going to keep how many sig figs? 1, 2, 3. Or 1, or 1, 2, 3, 4, 5. You might be thinking, 1 is the least number, except we know that this is actually not exactly 1. This is an infinite number of sig figs because it's the definition of a mole. A mole is equal to the molar mass. So I'm actually going to keep 3 sig figs because 3 is less than 5. Infinite is definitely more than 3. So we're going to keep 1, 2, 3. That 0 doesn't do anything. My final answer is 0.743. My unit label is moles of CO2 was produced in this chemical reaction. But now I want to know how many molecules of CO2 is this equal to. So I'm going to take that same number, 0.743 moles of CO2, and I'm going to convert it into molecules. I have moles on top. I'm going to put moles on bottom. I want to turn my moles into molecules. How do I do that? Remember that Avogadro's number tells us that there are 6.02 times 10 to the 23rd particles per 1 mole. And you know what are particles? Molecules. Molecules are a kind of particle. And so I'm going to put this number in front of molecules. 6.02 times 10 to the 23rd, I didn't leave enough space, divided by 1 mole. 1 mole is equal to 6.02 times 10 to the 23rd things, molecules, atoms, particles, even elephants. 6.02 times 10 to the 23rd elephants in a mole of elephants, which is entirely irrelevant to us right now. Moles, top and bottom, cancel out. Calculator, 0.743 times 6.02 divided by 1 is going to give us 0.743 times 6.02 times 10 to the 23rd. Handy dandy calculator tells us the answer is 4.4 0.473039606E23. How many sig figs are we going to keep? 1, 2, 3, 1, 2, 3. Infinite is more than 3. So we're going to keep 1, 2, 3. 1, 2, 3. 3 leaves that 7 a 7. 4.47. Remember that E23 means times 10 to the 23rd power. And my answer is going to be labeled in molecules of CO2. Good? Maybe a little bit good? All right. Let's look at this idea of relative atomic mass. So the masses given to us on the periodic table are the average or relative atomic mass. These are the same exact things. Relative atomic mass, average atomic mass, definitely the same thing. The mass given to us on the periodic table is relative or average atomic mass. And so we're going to talk a little bit about how do we even find these averages that we put on the periodic table. So it's calculated using the abundance of isotopes. Isotopes, remember, are atoms of the same element that have different numbers of neutrons and therefore different masses. We're going to take those different masses of the different isotopes and we're going to find the average. Isotopes are atoms of an element with different numbers of neutrons and therefore different masses. But I'm not going to just add them up and divide by the number of things because I also want to consider how much of each isotope is present on the Earth. Abundance is how much of each isotope is present on the Earth. And so if I'm looking at these 3 isotopes of hydrogen, these are all 3 isotopes of hydrogen. They're all hydrogen because they all have 1 proton. And if you have 1 proton, you are hydrogen. What's different about these atoms of hydrogen is they have different numbers of neutrons. This guy has 0 neutrons, this guy has 1 neutron, this guy has 2 neutrons. Because they have different numbers of neutrons, they have different masses. So this guy has 1 proton and 0 neutrons. Its mass is about 1. This guy has 1 proton and 1 neutron. Its mass is about 2. And this guy has 2 neutrons, 1 proton. Its mass is about 3. But to find the average, I'm not just going to go 1 plus 2 plus 3 divided by 3 is 2, because this guy with a mass of 1 is 99.985% of all of the hydrogen on the Earth. And this is only 0.015%. And this, there's so little of it, we round to 0%. It's negligible. There's so little. And so it wouldn't make sense to say that the average is 2 if almost everything is only equal to 1. So we're going to do some fancy math to find what we call a weighted average, a relative average, based on that idea of abundance. So what we're going to do is I'm going to turn my abundance into a decimal. Remember that percent means times 100. If I want to go backwards, I'm going to divide by 100, which means I'm just going to move my decimal place 1, 2 to the left. So step 1, turn your percent into a decimal. Move your decimal place in the percent 2 to the left. That's divided by 100. And so my abundance as a decimal, instead of 99.985%, is now 0.99985. We're going to do the same thing with this guy. Turn 0.015% into a decimal, divide by 100. Move that decimal place backwards, 1, 2, 0.000000015. I'm going to move the decimal place backwards 2 places. It's still just going to be 0, right? If you like, 0.00, but it's all the same. So that's step 1. Step 1 is to convert abundance as a percent into abundance as a decimal. Our next step, we're going to multiply the mass by the abundance. So I'm going to take that mass and I'm going to multiply it by the abundance, but I'm going to multiply it by the abundance as a decimal. So mass times decimal abundance. 1.007825 times 0.99985. With my calculator, 1.007825 times 99985 gives us a grand total of 1.007673826. How many sig figs do I keep? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. I'm going to keep 5. 1, 2, 3, 4, 5. That 7 is going to turn that 6 into a 7. And that's going to look like, oh, my eraser wouldn't turn on. So I'm going to turn that back to a 7. Good. All right. We'll do the same thing for this guy. Multiply the mass by the abundance as a decimal. So 2.014102 times 0.00015 is going to give us 0.000321153. How many sig figs do I keep? 1, 2, 3, 4, 5, 6, 7. 1, 2. We're going to keep 1, 2. That 1 is going to do nothing to that 2, so I'm just going to keep 3 and 2. I'm going to erase the other digits. Oh my gosh, my pen and the eraser is moving very slowly. Ha, there we go. Okay. Next up, we're going to multiply 3.06049 times 0. That's going to be 0, right? We can also just totally ignore it. So that's step 2. We're going to multiply the mass by the abundance. Step 1 was convert your percents to decimals by dividing by 100. Step 2, we're going to multiply the mass by the decimal. Good. Step 3, we're going to add up all the answers to step 2. So I'm going to take my step 1, I converted abundance to decimal. Step 2, I multiplied. Step 3, I'm going to take those answers and I'm going to add them up. 0.00032 plus 1.0077. 1.0077 plus 0.00032 gives us a grand total of 1.00802. And where am I going to round? Remember, when we add, we look at place value. So I have tenths, hundredths, thousandths, 10 thousandths. I have tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. 10 thousandths is bigger, so I'm going to round to the 10 thousandths place. Tenths, hundredths, thousandths, 10 thousandths. That 2 leaves that as 0. I can just get rid of that 2. If I can get my eraser to turn on. Oh my goodness. Okay, I'm just going to scratch it out since that eraser is not cooperating. So I'm going to have you look at this answer. This answer, 1.008. I want you to think about that 1.008, and I want you to go look at the mass of hydrogen on the periodic table, and you know what it is? It's 1.008. That's what our periodic table tells us is the mass of hydrogen. And this crazy hot mess of math is how we got that number. Good? All right, let's do another one just like this. So let's say that neon has 2 isotopes, neon 20 and 22. Given the following abundances of the isotopes in nature, what is the average? That average and relative are the same thing. Atomic mass of neon. So what we're going to do is step 1, turn our abundance as a percent into a decimal. We do that by dividing by 100. We're going to go backwards. 1, 2. Decimal place goes there. Go backwards. 1, 2. Decimal place goes there. So abundance as a decimal is going to be 0.9 and 0.1. Next step, we're going to multiply our mass number by our decimal abundance. And you might be thinking, but it doesn't tell me where my mass is. These numbers actually are the mass numbers rounded to whole numbers. And so I'm going to take neon 20, I'm going to multiply 20 by 0.9. 20 times 0.9 is going to give me 18. Take my 22 times 0.1, that's going to give me 2.2. We need to check our sig figs, right? So I'm going to do 18. I get to keep only one sig fig. That's going to be about 20 because that 8 rounds that one up to a 2. I get to keep one sig fig in this second guy because 1 is less than 2. And so I'm going to keep just one sig fig. That 2 is going to leave that 2 a 2. It's going to get to be 2. And now I add, and my answer is 22. But I need to check my sig figs again. When I add, I look at the last sig fig in each piece of data. That's the 10s, that's the 1s. That 0 doesn't count because there's no decimal. And so I'm going to round this to about 20. This is my answer. 20 is about the relative or weighted atomic mass of neon. And if you look at the periodic table, it's a little bit over 20. But rounded to only to 1 sig fig is going to be just about 20. So I'm going to have us do a little bit of a summary before we call this lecture done. So in your notes, I want you to write the steps that you should follow to calculate average atomic mass. Step 1, turn that percent into a decimal. Remember that we do that by dividing by 100. Or you can move your decimal place 2 to the left. Good, good. All right, step 2. What was that step 2? Multiply the mass by that decimal that we just found. Step 3, last step. What are we going to do? We're going to add all those pieces from step 2. And that's it. All right. Did we achieve all of our objectives? Yes, we did. We used the periodic table. We found out how to calculate masses of atoms, molecules, elements, and compounds. We talked about that crazy mole number, 6.02 times 10 to the 23rd particles in a mole. We used molar mass and the mole number to calculate the numbers of atoms or molecules in a sample. We looked at the CO2 and the sulfur. And then we finally calculated relative atomic mass, given the isotopes' masses and abundances. And remember that relative atomic mass, average atomic mass is a weighted average. So it's not just add and divide. It's looking at those percents that we turn into decimals, and then we multiply and add. Good? Good. Good work today, my friends.